Good day, everyone. My name is Lawrence A. Cornelio, a BSc History student from Bicol University, Palango, and today I will be discussing about my laboratory activity 2, which is plotting discrete time signal. So, here's my code now. Let's run it first and put it here then. So, first, we import NumPy for numerical operation and Matplotlib for plotting. Then we create a discrete time index and from negative 10 to positive 10 with a step of 1. This gives us 21 sample points. Negative indices represent time before 0, and positive indices represent time after 0. Then the unit impulse, also called the Dirac delta in continuous time, is defined as 1 at n equals 0 and 0 everywhere else. We use np.where is equal to n, np.where n is equal to 0, 1, 0, which checks each value. If n equals 0, put 1, otherwise put 0. This creates our impulse signal. So as you can see in our figure, at 0, the impulse is 1 and the value is 1 and everywhere else is 0. Next is unit step signal. The unit steps is 0 for negative time indices and 1 for 0 and positive indices. Using np.where, np.where n is greater than or equals 0, 1, 0, we set the value to 1 whenever n is greater than or equal to 0. This is the basic building block for processing. So here is our figure. As you can see, from 0 to positive, all signals are value 1 and negative is 0. Now next is for ramp signal. So the ramp signal increases linearly with time. It equals n for n greater than or equal to 0 and 0 for negative n. We use np.where n is greater or equal to 0 and 0. We use entry that where which places the actual and values when condition is true. This creates a signal that grows steadily. So here's, here is our ramp signal. So when the value is so when the n is 0 or negative, the value is 0, and when the value is positive, we can see a ramp-like signal. Now for exponential sequence. Exponential sequence. 0.8 raised to the power n multiplied by the unit step. For negative n is 0. For positive n, we compute 0.8 to the n as n increases, the value decays because 0.8 is less than 1. This models natural decay processes. So here is our figure. So when the value is negative, we can see the signal value is 0. And when it's 1, and when it's 0, the value is 1. And when n is increasing, we can see the plot is decaying exponentially. And last is the sinusoidal signal. Finally, a discrete cosine wave cosine of 0.2 pi times n. The 0.2 pi is the digital frequency. So here is sinusoid is equal to np.cos 0.2 times np.pi times n. This creates an oscillating signal that repeats every 10 samples. Cosine is fundamental for frequency analysis and communication. So here is our sinusoidal. So C from 1 is create a sinusoidal wave. Um, and so, so now we plot all the signals. So for plotting, we use signals, unit impulse unit steps, ramp, R and ramp, exponential 0.8 times raised to n, u times n expo, cosine cos 0.2 pi r, 2 pi, and sinusoids. And for each signal, we create a new figure with the figure, and Then plotting using PLT.stem and signal-based FMT. And so the base after you remove the baseline, we add the title, then X label and the time index, and PLTY label amplitude. Then we use PLT.show to display. And that's all. Thank you.